Okay, hopefully you had a quick break. I don't need to ever take a break. If you have those military night vision goggles, I'm the red glowing object. You see it all times a day. My motor runs like this even when I'm trying to sleep. I don't need a break. You have to have a break. You cannot sit for 2.5 hours. It's so bad for you. And what's worse is some of you are going to leave here and sit in front of a computer then for the rest of the day. So the question has been asked about textbooks and about online books. I truly don't care what textbook you use. I'd prefer you not get a new textbook each semester. Okay, some instructors require a specific one, but in the last few years, most of the instructors have been pretty lenient because they know you may change classes every semester in terms of instructors, and you can't be asked to buy a new book for a 3-semester class. So most instructors will allow you to use whatever you're using. Now, if you do an online book, don't rent. It's a 3-semester class. If you rent, you're going to end up spending significantly more for a rental than you would have for a book, and you won't have it at the end of the 3 semesters. No. If you're going to do that, at least buy the ebook. I don't like ebooks personally because I don't like sitting in front of the computer any more than I have to. I already am at the computer way too much. I'd rather sit outside. I'd literally rather go to the beach with my book. Hopefully none of you take your laptops to the beach. That's a bad idea. But if you have an ebook, then you're basically chained to a computer anytime you want to do math. The other thing, it's actually a sillier thing, is I hate scrolling. I don't have the patience to scroll. You got to go through 100 pages. I'm trying to find where it just flip. Yeah, it's just so much easier for me to do it. Plus, my eyes. It's really hard for me to look at a computer for any length of time, and it's really bad for you in general. You know that. Not just your posture, but your vision, the whole blue light thing, at night. So whatever you do, I'm okay with. Don't get a different book every semester. If you've had calculus before and you have the book you used last time, use that book this time. It's a source of homework questions. It's a source of practice problems. It is really hard for you to go to the internet and search for practice calculus. That's hard. You really have to have a textbook. And it doesn't matter what book, but you have to really have a source. Okay, you can't really be random. So we're going to now start the single most important concept probably in all 3 semesters of calculus, and that's the concept of limits. I remember as a calculus student, this took me so long to grasp. The algebra and everything else was trivial for me, but the concept of limit was so difficult for me to understand at first. I had a great instructor, but for some reason there was a disconnect in the explanation, and it wasn't until I started tutoring calculus a couple semesters later that I finally understood what was going on because I had to explain to somebody else. So the concept of limit is where am I headed? Not where am I getting to, but where am I headed? I may not be able to get there, but where would I be if I could? So we're going to start. And the notation we use, this is one of the rare times I actually use cursive. We write it like this. LIM as x approaches. Now, an arrow in calculus has exactly one meaning. It is not an ambiguous symbol in any context. It means approaches, never reaches. Do not use an arrow as an equal sign. I have people do that all the time. They'll say, well, my last instructor said it was okay. No. An arrow means it is not equal. So, first of all, 3 plus 4 equals 7. How do I interpret that next statement? 3 plus 4 gets really, really, really close to 7, but never gets to 7. It doesn't equal 7. It gets really close. This means it's not equal to 7. Don't use an arrow for an equal. Use an equal for an equal. Arrow means approaches, never reaches. But how close is approach? No matter how close you get, could you always get closer? Think of cutting that distance in half. I'm going to approach the wall. Okay, I'm pretty darn close. Can I get closer? Can I get closer? How close can I get? Keep going until I hit the wall? Nope, I got to stop before I hit the wall. Is there a closest point I can be, or will there always be one closer?
Always closer.
No matter what I do, can I always cut the distance in half, no matter where I am?
Yes.
Yeah. There is no, but where am I headed if I could get there? The wall. My limit is the wall. I never get to the wall, but boy, do I close in on the wall. So we say the limit as x approaches a of f of x equals L. We call L will be a finite value for now. We're going to talk about infinite limits later, but not yet. That's a couple lectures down the road. So from a pictorial sense, I just replaced all the black inks. Oh, excuse me. This morning I ran out of ink in every single pen I used. This is a removable discontinuity at the point a comma L. Nothing weird going on here. This one's boring. In both cases, the limit as x approaches a of my function, in both cases, the limit is L. The limit is not the functional value. The limit is where am I headed if I could get there. Did I get there in this case? Yeah. Did I get there in this case? No, I removed it. It's where am I headed if I could get there. So that always confuses people. But isn't the limit the functional value? Well, often it is. It can be, but the functional value, well, I removed this point and I placed it here. So this domain is now all real numbers, isn't it? But if I was driving down this road, it's a black hole. Is the limit still L or is the limit M? Just to make it clear, f of a is equal to M. But the limit is still this. As I get closer and closer and closer and closer, where am I heading? Does that make sense? The limit in all three pictures is L. In the first case, the hole is filled in at L. Second case, I removed it, and then third case, I just simply moved it. How many have ever seen Roadrunner and Coyote? I use a lot of analogies and a lot of things. You guys don't realize how much calculus you have been exposed to in your life, but you didn't necessarily know because you might have been kids. When I prove the most important mathematical theorem probably in the history of the world, the fundamental theorem of calculus, I have to use the garbage pit scene in the first Star Wars movie where the wall's closing in. That's actually what I use to prove it. Can't prove it any other way. When I'm first developing the notion of multiple independent variables, I use the Cat in the Hat from Dr. Seuss. Thing 1 and thing 2 both represent independent variables. The Cat in the Hat is the dependent function. I explain everything. It's absolutely clear. You've been, all your life, you've been exposed to calculus. You did not even realize it, okay? I can't prove the quotient rule when we get to without using Snow White and the Seven Dwarfs, because you're going to sing the song. And some of you may have learned a version of it. So we do this. Roadrunner and Coyote is the perfect example. Roadrunner and Coyote, you remember how the Coyote, he'd remove the manhole cover? You guys remember that? And so the Roadrunner would fall in? But the Roadrunner, like, this was brilliant. He would take the hole and he'd move the hole. Now, I think a few laws of physics may have been violated in there, but no one would ever, charge him. And so when the Coyote would come around, he'd fall in the hole he created for the Roadrunner. It's crazy. He's actually doing a perfect demonstration of a removable discontinuity, and then, that's the manhole cover. He just moved it. Okay? That's the manhole cover. It sounds crazy, but the concept of limit, we try to overanalyze. We try to do too much algebra. It's just, where would I get if I could get there? So along this line on the floor, you can't see it, there's a line on the floor. I'm going to remove a point. But what I'm going to do now is I'm in 3D. I'm going to lie down on the floor and start inching towards that. In other words, I can't see the hole. Up here, I can see the hole. When I'm lying on the floor, can I see the hole as I'm moving along this line? No. So if the hole wasn't there, this is where I would get to if I could get to it. The limit is where the hole is. Now, whether the hole's filled in or not does not change the limit. That, to me, blew my mind when I was a calculus student, first of all. You mean, how can both of these have the same limit? Because I never actually have to get there. It's where am I going if I could get there. So now, let's go back to the problem we did earlier. Remember this problem we just did right before the break? I want to know what is happening to the function as x gets closer and closer to 1. Okay, just evaluate it at 1. The problem is if I put a 1 into here, what do I get? I get 0 over 0. And here's how we write it. There is actually a formal mathematical way of writing it. 0 over 0 is not a number. It is a form. It's called an indeterminate form. There are 6 of them. We do 2 of them in this class. We do the other 4 in Calc 2. Indeterminate forms is what is the quotient taking on? What form? This is taking on the form 0 over 0. It doesn't equal 0 over 0 because that's not even a number. This means numerator and denominator are simultaneously approaching 0, which means that I can factor and cancel. I probably have a removable discontinuity. This is your favorite type of form because this is the only one that algebraically tends to be friendly. There are other indeterminate forms, particularly the exponential ones. The ones we do next semester, we do forms 0 to the 0th power, that one's crazy. 1 to the infinite power, that one's crazy. A difference where they're both approaching infinity, that one's crazy. And a product where one's approaching 0 and the other's approaching infinity. These don't have answers, you have to work them out. The 2 we do this semester are the 0 over 0, and the next week we do the infinity over infinity. And a lot of you will recognize it as something you actually did in pre-calculus. You didn't call it a limit, but you dealt with it. It's where the horizontal asymptotes of a graph come from. But that's next week. So I say, this is having this form, which means I believe I can factor and cancel. Can we factor and cancel? Yeah, we did it earlier. What does this factor and cancel as? Do you remember? Was it x plus 1? So I'm going to write x plus 1. Now, question. You're going, wait a minute. I had to write the disclaimer before. Didn't I have to write a disclaimer? I'm saying these quantities are identically equal for all real numbers, with the exception possibly of that one. I'm asking what happens as x approaches 1. X is never going to equal 1. And remember, 1 was not in the domain, but that's where I'm off the hook. X is approaching 1. It never gets there. So the limit of this quotient is equal to the limit of this statement. In other words, we can say that these quantities are identically equal for all real numbers except for 1. But I never get to 1. So now going back to the graph, this will hopefully make perfect sense. When we did this problem earlier, okay, as x gets closer and closer to 1, the y values are getting closer and closer to what? 2. As x gets closer and closer to 1, the y values are getting closer and closer to 2. Therefore, the limit is 2. Quantities approach, limits equal. I don't say the limit is approaching 2. No, the limit is 2. 2 is where I would get if I could get there. Everybody understand? This is very important that this is an equal sign. A lot of folks will say approaches, which means you're not done. Okay? But that's not even, it doesn't matter. As I got closer and closer and closer and closer, y values are, if it helps you mentally, never really do this. Pick values, if it helps you conceptually, pick values of x that are really close to 1. Okay, at 1.00000000001, then this would be 2.000000001. Got it? If x is 0.9999999, then this is 1.999. No matter how close I get to 1, that value is getting closer to 2. My limit is 2. But at that point, I can literally just take the 1 and stick it in there. That's nice. This is your favorite type of problem. This is the removable discontinuity that came from a rational function where I could factor and cancel. That's your favorite problem. That's not the only problem. That's just one problem. Excuse me. We're going to be doing things soon that involve trig functions. Those are a bit more complicated. All right. What if I have something like this? The limit as x goes to 16 of the square root of x minus 4 over x minus 16. Is this a rational function? I gotta think, what's the definition of rational function again? The answer is yes or no. It's not maybe. Is this a rational function? We love rational functions. Is it a rational function? No, because this is not a polynomial. Why is that important? Because it means I can't do the factor and cancel. Can't use synthetic division on the numerator. Oh, shoot. All the things I could do to that one, I can't do to this one. Now, if I replace an x with 16, aren't numerator and denominator both approaching 0 again? Do you all agree that this one's doing this? Yes. Even though I can't factor and cancel directly, there's a really good chance that I might be able to manipulate this. In other words, I might have to do something. Do you remember what we did with the trig quotient a little while ago? We multiplied by a conjugate and we manipulated and did stuff. The problem child here is this. The problem child cannot come from the numerator. If my denominator were not approaching 0 and my numerator was, that just means my quotient's approaching 0. 0 over non-zero, I'm pretty sure, is always 0. The problem is never the numerator, it's the denominator. So x minus 16 is the problem child. Is there a way I could get an x minus 16 on top? Is there a clever one amongst you? Come on, somebody's got to be clever. At least I only need one clever person. Which is the conjugate, but not of the denominator, of the numerator. First of all, here's a really big question. Is that a legal move? Yeah. A lot of times we can manipulate a quotient because we multiply numerator and denominator by things. We do things all the time. In baby algebra, you had to get rid of things, so you multiply top and bottom by variable-ish things. But every now and then you've got an extraneous solution. You did something, the only way to solve the problem, or you multiplied through by a common denominator, you did all these crazy things, but sometimes it didn't work. You go, why? Because there's a couple of absolutes. You can never multiply or divide by something that can potentially equal, what? 0. Because I will completely change the nature of the problem. I'm going to show you that in a moment. I can never multiply or divide by something that can potentially equal 0. I will change everything. Root x plus 4, can that ever be 0? No, it's strictly positive. In other words, is that legal? Absolutely. If I multiplied by root x minus 4, that could potentially equal 0, couldn't it? That's where I would get in trouble, but that's not what I did. I didn't need to do that. Now, in doing that, what is my new numerator? This is beautiful. X minus 16. That is a good thing. Do I want to distribute on the bottom? Oh, heck no, because then I'd have to factor again. No, don't distribute on the bottom. You already have an x minus 16. Now, one of the most common errors that people make with limits is not that they get the wrong answer, it's that they answer too soon. You didn't tell me the answer here. Why? Because numerator and denominator are both approaching 0. You told me the answer here because there's no longer a denominator. I can't give you the answer right now because both numerator and denominator are approaching 0. But if I cancel, I'm saying this quotient here is identically equal to this quotient here for all real numbers except
16.
Perhaps 16. But it's okay because I never equal 16. Why did I say except for 16? Because that's the thing we canceled. The removable discontinuity came when the root was 16. So these quantities are equal as long as x isn't 16, but x isn't 16. It's only approaching 16. This is not a problem child anymore, is it? That's a happy statement. So now as x approaches 16, what is this quotient approaching? 1 over 8. So I say the answer is 1 over 8. Isn't that cool? You like that? I mean, you gotta like that. It's kind of cool. Now, do I need a graph to explain this problem? No, because I really don't want to graph this. This is ugly. Could I? Yeah. What I would do is, if I wouldn't do my graphing calculator, I'd just do Desmos or something and get a big picture and look at it. You don't need to. But what we have is a removable discontinuity. Whatever the graph of this looks like, this is the exact same graph with the point 16,1/8 removed. It's literally the whole. If I asked you to graph x plus 1, there's no hole. It's just a line. But the graph of this guy has a hole right here. So we say you plucked the point and you just took it out. You removed it from the problem. That's the easiest way to remember. That's why it's called a removable discontinuity. We're going to learn there are 4 types of discontinuities. We're not going to do all of them today. This is the first one. This is our favorite one. There are a whole bunch of different ones, including asymptotes and evil creatures like that. Okay, question? Good. Okay. When you have a question, I'd rather you ask it now than the after class questions like, why didn't you ask it in class? Every now and then, somebody will come by my office and have the best question I've ever heard. And I'll say, can you wait till class to ask that? Why would I say that? Why would I ask you to wait till class to ask your question? Because otherwise he's the only one that got the answer when every one of you really needs to hear that question because a really good question, therefore you all get the answer. Yeah, the really good questions I'd rather ask in class because then everyone gets the benefit of the explanation. Because sometimes that really good question, you'll have it. It's not now, you'll have it later. And I'd really rather not answer it 30 separate times. Okay, so far so good? That's kind of cool. All right, now, does it always have to be numbers? Grab an example of something else. By the way, the majority of the limits that we do in this class will not be numerical. They'll be functional. Okay, here's a good one. Which one? Hold on a second. No. Well, that's kind of weird. But doesn't x have to be going to 0? Nope. Nope, x is just x. I'm having a go to 0. Okay, so if I replace a with 0, then my numerator is clearly 0. Agreed? And so is my denominator. Is this a rational function?
Yes.
That means absolutely then I can cancel what in the end? A. Because A is the thing going to 0 on bottom. I'm going to be able to cancel an A. I don't see it, by the way. I can't see it now. You're not supposed to see it now. I'm going to have to expand and manipulate. But this is my money back guarantee. You're going to be able to cancel an A before the problem's over. Again, because numerator and denominator are both going to 0 when A goes to 0. So if it helps you, I could cancel an x minus 16 because x was approaching 16. I can cancel an A minus 0 because A is approaching 0. That's why it's an A, not something else. Well, can I square this guy? I'm going to be lazy right here. X squared minus 2ax plus a squared minus x squared. Okay. Can I combine anything on top?
You can get rid of the x squared.
All right. Can I manipulate this one? Well, every term on top has an A.
You take that A out from the top.
So do I factor the A out and then cancel it? Yes, but that's 2 steps. Without skipping a step or doing a single step in your head, I want you to have the simplification in 1 step. Most of you didn't learn this. Let me show you 2 ways of doing this in 1 step. Question?
There's supposed to be 2.
Did I lose? Oh, thank you, I lost the 2. You're right. That should be what? Negative 2ax. Good catch. That will matter. There's two ways I can do this in one step. This is one that nobody ever thinks about or realizes it, but you're going to do this one later on. Do not factor it. That's one step. Then cancel it 2 steps. Multiply top and bottom by 1 over a. And what will you get? This is one way to do it. What will I get? Negative 2x plus a over 1. I'm not going to write over 1. You can write over 1. Yes, it's correct to write over 1. I never do. The second way, here's the one thing I don't ever do. This is absolutely correct. This is what all students do. This is what all textbooks do. This is correct. Now I have to take another step to write the simplification. It's absolutely correct, but it's 2 steps. The first step was completely redundant. You know the A is going to cancel. Don't take a step to do it. Have this be the next thing you write, not the second thing you write. Do you see what I'm getting at when I said sometimes we take steps that are completely unnecessary? This is how we were all formally taught to do it. Never did it that way. It takes too long. Might make a mistake. Every time you take an extra step, you might make a mistake. Now, am I done? I haven't taken the limit yet. I think I can do this one. As a approaches 0, this is approaching. As a approaches 0,
Minus 2x.
negative 2x. So here's a case where my limit was not a number, but was a function. Just so you know, as we go on, the vast majority of limit problems that you're going to do, your limits will be functions. The vast majority. We started by doing ones that were nice and my answers were numerical, but the answer can be a function. There's nothing weird about that. Did I do the same process on this one that I did on the others? More or less? Yeah. Okay, now I'm going to show you an evil one. Sometimes the evil ones are fun. You know, you like to root for the bad guys. Everybody understands that sometimes. I mean, oh my gosh. I can't tell you how many times my oldest son, when he was really little, he'd watch the Darth Maul. It was his favorite. You know, I mean, who doesn't root for Darth Vader? I mean, he would root for the dinosaurs in Jurassic Park to eat the people when he was like 2 years old. He always roots for the bad guys because sometimes the evil guys are fun, but sometimes the evil ones are they're not fun. The next one's not fun, but it's absolutely necessary for our overall understanding. Okay, I'm going to start with a simple one. This is what is called a piecewise function. We do not spend a lot of time in calculus on piecewise functions because they're actually quite difficult to do calculus on. But they're fantastic for explaining things.
No, that's not microwave.
Yeah, it's x squared. When x is greater than or equal to 1, it's x minus 1. This is typically how you have the comma, semicolon, you have to somehow. So I've got a piecewise function. I'm defining a function in 2 pieces. Without doing any work whatsoever, what is the domain of this?
All real numbers.
All real numbers. So this ought to be easy. Except I would like to ask, what's the limit as x approaches 1 of f of x? Now, normally I wouldn't draw a picture. I'm going to draw a picture in this case, and then I'm going to do the math because I think this will be so much easier to understand. The reason I say don't draw the picture in general is what if I made these two really complicated? Do you really want to spend time drawing the picture? Because we can go directly to the math without drawing the picture. But if I drew a picture of this, it's y equal x squared. So it starts here, goes through here, and like that. And then y equal x minus 1. Oops, does that look fairly accurate? It's accurate-ish. Okay. I'm asking, what is x approaches 1? Now we have a problem here. All right. So The other day, we were kids in the elementary school together. You know, we used to go down to the train tracks. Remember that? We'd throw rocks at the train and then we'd run when they'd get mad at us and all this. So after a few years, we run into each other and we say, "Oh, do you remember when we were kids? Let's go down to the railroad track and revisit. Except you live in the north part of town, I live in the south part of town, and the railroad tracks are kind of in the middle." So we plan on meeting the next day at the railroad tracks. Only problem was in the middle of the night there was like a 8.0 earthquake, and the railroad tracks were. So you showed up at the railroad tracks, and I showed up at the railroad tracks, and I waited, and you waited, and like, oh great, I stood up at the railroad tracks, you know. So who was right? Or is this an impossible situation? I'm asking you, what happens as X approaches 1? This is the railroad tracks that got split because of the earthquake. This is a completely different problem than the other ones. This is where we're going to introduce the concept of one-sided limits. Okay? So the notation in this problem here, I'm going to ask you, what is the limit as X approaches 1 from the right? And this is how we indicate this. Regardless of what the number is, approaching from the right, you put a plus sign, meaning you're approaching it from numbers bigger than that number. So they have to be bigger than 1, approaching 1. Okay? The second part, I'm going to ask you to approach it from the left, which means you're approaching it from numbers smaller than and working your way back to the 1. Okay, you all with me on this? Now, from the right of 1, what is the function when I'm to the right of 1? This is to the right of 1. Do you agree that that's my function? My function is x squared. Can you easily evaluate this limit without doing any work? As x approaches 1, what does x squared approach?
1.
1. Okay, piece of cake. Now, I would like to approach 1 from numbers to the left of 1, which means I'm approaching along this
0.
curve, which means I'm approaching along this function. So I'm going to replace f of x with what f of x is when x is less than 1. F of x is x minus 1. And what would this limit be?
0.
Okay, Houston, we have a problem. Okay, you showed up at 1, I showed up at 0. The question is, what is this limit? We haven't addressed this. Anybody want to take a chance on this one? The worst thing, if you're wrong, I'll throw this at you, but I'm a really lousy shot. So,
It doesn't exist.
does not exist. Perfect answer. There are 3 possible answers to every limit question. The first 2 problems we did were our favorite ones. Finite. The limit is a finite number. The second one, which is also very common that we're going to explore next week, is the limit can actually be infinite. I'll give you really simple. I want y equal x squared, and I want x to get bigger and bigger and bigger and bigger. What's happening to y? It's getting bigger and bigger and bigger. Is there an upper limit? No, it's infinite. A limit can be finite, it can be infinite, or it can not exist. We say d/any. We don't like d/any. We think we did something wrong, but that's actually a very common answer. So the answer I'm going back to here is d/any. Why is it d/any is more important? So we did not address one-sided limits in either one of the problems that we did, or any of the problems we did earlier, because we didn't need to. You only look at one-sided limits if your function is changing, like a piecewise function. My function didn't change left and right of the number. Doesn't matter if I do left, right, everything's fine. But if I have a function where on the left and on the right might be different, then I have to consider one-sided. So here's something we say this way. The limit as x approaches a of f of x exists. How many are familiar with IFF? Do we know what that stands for? If and only if. That's kind of a universal shorthand. If and only if. If and only if is called a biconditional. If A, then B. If B, then A. So A, if and only if B. They're both true or they're both false, in other words. This limit exists if and only if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. Now, I did a problem earlier where I gave you a hole and then I filled in the limit somewhere else. But the function remained the same on both sides. I didn't need to do one-sided limits in that case. But I do in this case because the function on the right and the function on the left are completely different functions. Let me change this. Change that to any real number other than 1. Make it -3. Make it +5. Would I have any issues in this problem if that number wasn't a 1? Would it be an easy problem if it wasn't a 1? Yeah, because I'd just be right on the graph. But because I chose the place where I changed the definition, right, from one function to the other, that's where it might be iffy. How can I make it so the function exists, or so the limit exists? What if I made this x squared -1? What would that do? Would that move this piece down? Would that make the limit exist? Yes. Would I still have to do one-sided limits? Yeah, because I have two different functions. So in a piecewise function, you always do one-sided limits in this case. Now, here's one of the nice things. This limit did not exist, but both of the one-sided limits did. So for the most part, one-sided limits generally exist. Generally exist. There is an exception. This is one of my favorite exceptions because it stumps everybody. What is the limit as x approaches 0 of the square root function? Well, that's easy. That's easy, isn't it? It's the last thing we're going to do today. Obviously, the answer is what? I'm winking at you with my
Should
left
be
eye.
there.
You know something's up when it's the left eye wink every time. The answer is obviously what?
Does not exist.
Does not exist. Good. What? Why is it a D&E? Because there's nothing to the left. The limit from the right is 0. The limit from the left does not exist because I'm outside the domain. That's why I said this one is tricky. This stumps everybody, but after the fact you go, oh, perfect sense. Because the domain of this is 0 to infinity. There's nothing to the left. So what if I change this to a plus sign here? Now what's the limit? 0. Good. That one should be easy. But the overall limit not existing would stump us because we weren't expecting that. All right? Can you go ahead and press the red button? I'm going to stop the recording.